Okay, so this is the first of two videos on periodic trends, and what we're going to be discussing in these two videos are basically how certain properties of atoms vary across the periodic table. Things like how does the size of atoms varies across a period and down a group, what factors affect that, the size of the ions with respect to each other and with respect to atoms also. And we're going to talk about how these how even the first ionization energies vary across a period down a group, and electronegativities also. Now the reason why they clump together is because all of these four are going to be dependent on one or two basic principles of physics, and those will come into play when we look at individual atoms and atoms across periods and down groups. Now what kind of those ideas are important? Now what I have on the right is an atom of sodium, one of my favorite atoms. Now the reason I have it here is because, just to give you a summary of what we're going to be discussing, what you must realize is that all of these four properties will depend on how strongly the outer shell electrons experience the force of attraction from the center of the atom. Basically, all of these four properties will be dependent on the force of attraction this outer electron or anybody on the outermost shell will experience from this center positive nucleus. And a few terms that will come in handy are: one is the fact that the charge of the nucleus is called nuclear charge. Okay, that is, nuclear charge just refers to the number of protons in the nucleus. There will be, and if Z is used to denote that, then ZEFF is one way to talk about effective nuclear charge. And it's something that we mentioned in the last video, and I will talk about it again. Effective nuclear charge is basically the net nuclear charge that the outermost electron will feel from the nucleus, because what happens is that the outermost electron is not only feeling this attraction that I'm drawing right now. That isn't the only attraction it's feeling. It's also feeling the repulsion from each individual electrons, and I'll draw them out for you in a different color. Yeah, green. So basically all these pink dots represent electrons, and what's happening is each of these electrons are also repelling each other and the outermost. So this guy is fighting off the repulsions from the other electrons, even the ones far away, obviously lesser repulsion, and also having to experience the attraction from the nucleus. And what happens is that we got to study how this varies because of distance and the other guys present. And obviously this was the only force. Then the greater the force, the more this electron is pulled and the more inwards it is. So obviously nuclear charge is a very big factor that plays in the size and energies, because size of atom means how big a sodium atom would be compared to other guys. Now size of ions, obviously when sodium loses the electron, the outermost electron, it becomes sodium plus. So what size is that? First ionization energy is basically the idea that first ionization energy is the energy required to remove this outermost electron. Now how does that energy vary for sodium versus, let's say, magnesium, the guy right after it, or for sodium versus potassium, the guy right below it? So we'll discuss that. How does that energy change? Because what we know is that, generally speaking, that it is harder to lose for magnesium to lose the electron than for sodium. So is there any way we can explain that? And why is it that, and you guys do this in O levels, that down a group it becomes easier to lose electrons? So why is the first ionization energy of potassium less than that of sodium? We'll discuss that also. And all of these factors also affect electronegativities, which will lead us into the next chapter anyways, Oberlin bonding, because electronegativity is the ability of an atom to pull shared pair of electrons towards itself. So all of these four factors will be dependent on the net attraction the outermost electron experiences from the nucleus. And we won't have to worry about one particular. All we are more concerned with is comparing all of these across a period down a group, all of these across a period down a group, and the same for ionization energies and the same for electronegativities. We're not looking for absolutes, we're looking for trends across the periodic table. Yes, there are also chemical trends, but those we'll do much later. We're doing this right now because this will also lead into the next chapter, which is bonding, which will then talk about intermolecular forces and stuff. So we need this stuff for that. Anyways, so let's start digging into what kind of ways these forces can vary worse with different atoms. For example, we start off with sodium and magnesium first. Okay, so on this slide, what I have for you is the two atoms of sodium and magnesium, one atom each, and drawn in their full basic configuration of electrons, the nucleus having 11 protons, 2 here, 8 here, and 1 for sodium, and 2 here, and 2 electrons here, then 8, and then 2 for magnesium in the outermost shell. And the reason why I'm done this is because I want to be able to compare the force that this particular electron feels from the nucleus, and so was this one. And how do these two forces vary? So here I'm drawing that force for sodium and magnesium, and we're going to talk about how these two forces are not exactly equal, and one is stronger than the other, and what makes one stronger. And if you can understand the variation of this force, that can help us determine the size of atoms, because this force is for the outermost electron, and the atoms are really just a nucleus and electrons around it, and the closer the electrons can be to the nucleus, the smaller the atom would be. Obviously, the way I've drawn this, I've not drawn them to even in terms of the size, so that you'll see both of them having same size right here, but that's not the case. In the real world, we know that magnesium is slightly smaller than that of magnesium's atom is slightly smaller than that of sodium's, and we'll talk about that right now. But a few things to note. So we're going to talk about this. The nucleus will be attracting the outermost electron, and the inner electrons, the ones inner, have the most repulsion for the outermost electron. Yes, the one in the same shell will repel this, but it's the inner ones that have more repulsion. So I'm going to use a little different arrow, let's say blue, to talk about this repulsion, pushing these electrons away. So basically all of these are going to push the outermost electron away from sodium. And same here, this repulsion, this repulsion. If you notice, I'm just drawn a lot of repulsions here, and there are more obviously, but I don't want to crowd this up. Same here. So basically, for each electron that I've drawn here is being pulled by the nucleus and being pushed away by the electrons, and we've got to figure out the relationship between the two, the pull and the push. Now the pull comes from the protons in the nucleus, because the protons have a plus charge, and for that I would really like for you guys to remember this term. A couple of terms I'm going to write right here on the board, on the slide, so that comes in handy for you to use. One of them is called nuclear charge. Now nuclear charge is the charge of the nucleus, and instead of saying proton number again and again, I'm going to refer to in terms of nuclear charge, so that the word sticks with you. The fact that this is a charged particle. The nucleus is a charged particle. It has a plus charge, and we refer to that plus charge as nuclear charge. That means for sodium, this guy is 11 plus. The nuclear charge of sodium's nucleus is 11 plus, and the nuclear charge of magnesium is 12 plus. So basically, effectively, this electron is feeling the pull of 11 plus, and this is feeling the pull of 12 plus. Now, if that was the only force acting, you can easily assume that which force is going to be stronger. The 12 plus is going to attract the electron more than the 11 plus, because there's greater charge, so greater attraction. And generally that's the case. If nuclear charge is more, then the attraction for the electron will be more. But you also want to ask me, well, what about these repulsions? Now, to account for the repulsions of inner shells, there's a term used for that also, and that term is called shielding effect. Now, shielding effect, also known as screening effect, is the term we use to represent how the inner shells shield the outer electron from the effect of the nucleus. And the reason why inner shells like these and these can shield is because the inner shells tend to do a good job of repelling the outermost electron. So what they're doing is they're repelling the outermost electron, and by the repulsion, this attraction decreases. Same here, this repulsion said this attraction decreases. Now it's the same in both cases. There is repulsion, and that's going to decrease the attraction, and the repulsion comes from having inner shell electrons. Now if I count the inner shell electrons in sodium, you got 2 in the first shell and 8 in the second shell. In magnesium, there are 2 in the first shell and also 8 in the second shell. Both of them have 10 electrons in the inner shells, and those 10 are repelling this outermost electron. Now in magnesium, those 10 are not just repelling this electron, they're also repelling this one, the other, because in magnesium the outermost shell has 2 electrons. So they're also repelling this one, but their repulsion is independent. So basically this repulsion that I'm drawing right now is independent of this repulsion. So they'll keep repelling both sides. Now, since both of them have only 10 electrons in the inner shells, what we say is that both of them have the same shielding effect. that because they both have two inner shells and the inner shells contain a total of 10 electrons in either case, so both experience the same shielding effect. There is no increase in shielding effect going from sodium to magnesium, and the reason why I'm talking about going from sodium to magnesium is that sodium's proton number is 11 and magnesium's is 12, and they are both in the third period of the periodic table. So this is the element in group 1 of the period 3, and this is the element in group 2 of period 3. So they come one after the other in period 3. And when I'm going to cross these elements in period 3, what's happening is the proton number is increasing, which means the nuclear charge is increasing. And when we go across, the shells don't increase at all, so the number of inner shell electrons remain the same, which is in this case both of them will have the same shielding effect. There's no increase in the shielding effect. So when there's no increase in the repulsion, but there is increase in the attraction, what you can clearly deduce from that is that this fellow in magnesium is going to be pulled more by the nucleus than that in sodium's case, which means this attraction is slightly more than this one found in sodium, which makes this attraction more, which makes this harder to be lost. So three things together working out here. So when you pull these together, two things will happen. This whole shell will get closer, which means magnesium will get smaller than sodium because it's closer. Both will be pulled closer. So the whole shell, the outermost shell magnesium, will be smaller than that of sodium. And secondly, this electron, if you want to remove this electron in magnesium versus this in sodium, the one in magnesium will require more energy to be removed, because that guy is being pulled in a little more. And removing electrons from the outer shell, the first electron, that's called first ionization energy, or first IE. Now we will look at these values also, but this is about near about 500 kilojoules per mole, and for this is about near 700 or 650 kilojoules per mole, telling you that the energy required to remove the first electron in magnesium is more than that of sodium. So the first thing, and this is important that you realize, is that because both properties, size of the atom and first ionization energy, are dependent on the fact that across a period nuclear charge is increasing and shielding effect is remaining the same, because the inner shell electrons are not increasing. So across a period nuclear charge is increasing, shielding remaining the same, so the only increase is the force of attraction. So the force of attraction for the outermost electron increases for the same number of shells, which means magnesium is smaller and has a greater ionization energy than sodium. And this trend continues all throughout the period, starting from sodium all the way to argon. And I'll show them all three to you. Now I'm going to show you argon on this side. I'm going to scroll to the right so that I can show you guys argon also. Now I'm going to zoom in just a little bit so I can show you all three together. Now here, what's happening is as you go across period 3, you start from sodium, whose atomic number is 11, magnesium, whose atomic number is 12, and you got aluminum 13, and so on, other elements. And you got a chlorine in 17 and argon 18, and we'll talk about chlorine also in a bit, but right now I'm focusing on the whole group and a whole period, and showing you as you go across the period, what's happening here is that the outermost electrons are increasing. You go from 1 to 2 to 3, 4, 5, 6, 7, and 8 in argon, and the nuclear charge is also increasing. Now what that does is that the attraction for the outermost should increase, because there's no increase in inner shells, because in argon also this is the inner shell. First inner shell is 2 electrons, the second inner shell is 8 electrons, so the inner shells are 10. Yes, you got more electrons in the outermost shell and they will have repulsion, but the biggest problem is the repulsion from inner shell electrons, and we call that shielding effect, like I was saying. So for argon the shielding effect remains the same, but the nuclear charge is increasing. It's going from 11, 12, 13, 14, 15, 16, 17, 18. So what it does is that this outer guy is attracted the most by the nucleus amongst all of these 8 from period 3. So this force that I'm just drawing is the strongest for argon in period 3, of sodium, magnesium, aluminum all the way to argon. So this force is the strongest, which should do two things. It should make this electron the hardest to remove. So basically from all of the elements in group in period 3, Argon's first ionization energy is the greatest because the electron is hardest to remove, and the reason why it's hardest to remove is because it's being pulled most by the nucleus. And second, by that definition, the atom size should be smallest for argon, and it is. For all the atoms, argon is going to be the smallest atom. The only problem we'll discuss later is the flaw in the measurement for argon. Otherwise, if there was no flaw for the measurement of argon, and for today just assume that there is no flaw, that as you go across a period, argon, the size of the atoms decreases and the guy at the end of the period is the smallest guy. So across a period you will notice two things, and then keep this in mind because we will solidify this idea later also, that across a period, what's going to happen? What's going to happen is that nuclear charge is increasing. The shielding effect generally remains constant, remains the same. Therefore, atomic size, which is the size of the atoms, sorry, that was fast, the size of the atoms decreases. Let me erase that, decreases. So that decreases. And first ionization energy increases across a period. So the guy at the end requires the most energy to be lost, and the guy at the end is the smallest to be lost. And let me zoom out to give you the big picture right here. That is the big picture where we discussed across a period, shells remain the same, inner shells remain the same, therefore shielding effect remains the same. But the proton number increases, so nuclear charge increases, which means the attraction for the outermost electron will increase, which means that the energy required to lose the outermost electron increases across the period and is greatest for the guy at the end of the period. And also the atoms get pulled in more, the whole electron cloud gets pulled in more, and the guy at the end of the period is the smallest guy. So across the period, atomic size decreases and ionization energy increases, and both because of the same reason. And the third factor, which is electronegativity, and I'm just throwing this in here right now, even if you don't remember it, because this is a revision, so you should remember it, and we'll discuss electronegativity a little later, but electronegativity also increases across a period. So all in these three factors are changing because of the same thing, that across a period nuclear charge is increasing and shielding effect is remaining the same. And here is a representation of what's happening to the atomic radius across a period. And if you can see here, from sodium, magnesium, aluminum, silicon, the size of the atom is going to decrease. This diagram is the representation of what is happening to the atom across a period. And that's not just true for period 3, which I've drawn here. It's true for period 2, period 4, period 5. The only reason why we do period 3 is because the Cambridge syllabus is adamant and it wants to discuss period 3. And the reason for that is period 2, the guy before this in period 2, which is basically lithium all the way to neon, lithium, beryllium, boron all the way to neon, is not very indicative of all the periods below it. So period 3 and below are all similar in their trends, but not to say that for all, period 2 included, size of the atoms is going to decrease across a period. And I've just discussed with you why, so remember this. Now you can also draw this graphically, and if you're looking for trends, then generally that's what the case is, that the size is decreasing across a period, except for argon's issue in measurement, and we'll talk about that in the next video. Right now I'm explaining the basic theory behind why does the size decrease and why does the ionization energy increase across a period, down a group. Tomorrow we'll do specifics in the next video. Thanks. Now on the next slide we'll talk about how does the size and ionization energy vary across a period. Vary down a group, because across a period we know that atomic radius decreases and first ionization energy increases. Now we'll discuss what happens to atoms down a group, and we'll take a look at group 1 for that. So over to the next slide. So here we got two atoms from group 1, sodium and potassium, and in all their glory, where all the electrons in the shell shown. In sodium they've got 3 shells, 2, 8 and 1. 11 protons in the nucleus, 11 plus nuclear charge. Potassium, you got 19 protons in the nucleus, so much greater nuclear charge. But what potassium also has, that sodium doesn't have, is 1 extra shell, because it's got 2, 8, 8 and 1. And so we're going to discuss how this outermost electron is being pulled by both the nuclei. Now for sodium I'm drawing it here, and for potassium here. And the difference now is not just the fact that potassium has a greater nuclear charge, It's also the fact that there are more shells. So it has more shells, the electron is definitely going to be further away. So that's by default, because it's got to layer in more shells. And the reason why shells increase size is because आपस में shells are going to repel the electrons. Like each of these electrons are being repelling each other also. So shells have to, by definition, push each other apart because they are all negative. So the shells are pushing each other away. So the electron in the extra shell for potassium is going to be further away than that in sodium. And that matters. So by right off the bat, potassium is going to be larger than sodium without even having to worry about nuclear charge. And this repulsion is much greater than the additional attraction this 19 plus has, which is why this is a larger atom. But because if the attraction was even more than this repulsion, obviously it will put it in more. But the inner shell's repulsion is pushing this electron outward, making the size larger. And therefore, when the reason why it's larger is because those repulsions are greater than the additional attraction that the 8 protons are going to give potassium. So potassium, the guy below sodium in group 1, because if you look at group 1 on the right, I'm just writing it down. You got lithium, sodium, potassium, rubidium, and I think cesium. But yeah, I'm just going to focus on these. I don't even know rubidium hai ki nahi hai. Sorry, I don't know all of my periodic table elements by heart. So group 1, these guys. So down this list, the nuclear charge is increasing by 8, 3, 11, and 19 because 8, 8, 8 बढ़ रहे हैं. The shells are increasing also. This has 2 shells, this has 3 shells, this has 4 shells. And so the inter-electronic shell repulsion is going to be greater for potassium than the increase in attraction by the nucleus. Therefore, the electron is further away in potassium than in sodium. So this, right off the bat, the size for potassium is larger. So that's easier part. The second part is that trying to remove these electrons, because in O levels we've done reactivity. So for group 1, the reactivity is to be able to lose this first electron, or the energy required to lose the first electron, which is also known as ionization energy. And so one way to measure this attraction is by ionization energy. And what we've realized is that the ionization energy is decreasing down the group. Not by much, but slightly decreasing. Even though there is a greater pull by the nucleus down a group, because this is this is above the group and this is below the group. Greater charge, more attraction. But what we've noticed is that the attraction is overpowered by other things, which is the electron is further away, and more importantly, this electron is experiencing greater repulsion from other guys, hence an increase in what we call the shielding effect. So when you go down a group, definitely what's happening is nuclear charge is increasing. So I'm going to write that nuclear charge is increasing. But since the number of inner shells increase, because for sodium, the outermost key inner shells are 2. And so the inner shells key electrons go from are 10. But for potassium, the outermost is in the 4th shell. So there are 3 inner shells. That totals 18 electrons before the outermost is seen. So down the group, the number of inner shell electrons are increasing, which means one thing, which means shielding effect is increasing. Now, why is that important? Because for groups down the group, for atoms down the group, what we have discovered is that as you go down the group, the nuclear charge will increase, but the increase of that is outweighed or counterbalanced by the increase in shielding effect and distance. Both are increasing because the number of inner shells electrons are increasing. And that's why down the group ionization energy will decrease, and even size will increase and ionization energy will decrease. So down this group of group 1, what you should realize is that atomic radius is going to increase, and first ionization energy is going to decrease down the group. And the reason why it decreases, and please remember this, is that even though nuclear charge is increasing, its increase is counterbalanced or opposed by the increase in shielding effect, which is caused by having more inner shell electrons, which also increases the distance the electron is away from the nucleus, which makes it slightly easier to be removed, even though there's more charge attracting it. But the net attraction is less because it's further away and experiences greater shielding. And so for the questions, the answers, they generally ask you, please explain the trend of first ionization energies down a group. And you say, down a group, even though the nuclear charge is increasing, its effect is counterbalanced by the increase in shielding effect and atomic distance. Both of them, both electronic distance from the nucleus, both of them are increasing because the number of initial electrons are increasing. And why are they increasing? Because you're getting more shells. So that's important for the exams, and why trends of ionization energy is down a group. So now we've got both trends of ionization energy across a period and size across a period, and both atomic size and ionization energies down a group. So let's put them all together in the next slide. So here I've got some atoms from the periodic table and drawn in the respective sizes so that you can understand and you can remember the difference in atomic radius. So you got period 2 elements here. They across the period are decreasing. I have purposely not drawn group 8 or the noble gases because their measurements are flawed, and we'll talk about that tomorrow. But across the period, this atomic radius is going to decrease for period 2 and even period 3. Period 4 and 5, I don't have them because we've got transition elements here, but we do have group 1 and group 7 down the group, so that even for all the groups, group 1, 2, 3, 4, 5, as you go down the group, the size is going to increase. But across a period, the size is going to decrease. Even for group 17 that we study, or no, the halogens, 7 or 17, that's what they call them now. As you go down the group, the size is going to increase. And the size increase because there are more shells. There are more shells, which means that the electronic repulsion is greater and overcomes any nuclear charge more that chlorine might have for fluorine than fluorine. That's why the size gets larger. And across a period, the size decreases, which is why iodine is smaller than rubidium. Because across a period, nuclear charge is increasing, shielding effect remains the same, therefore size will decrease. The other thing is that as you go across this period, in addition to atomic size, what's happening is, on a general trend level, the first ionization energy is going to increase. With a couple of bumps that will come in the next video. And down this group, the first ionization energy will decrease. And the reason why the ionization energy decreases down a group, we just discussed, is down the group there's an increase in nuclear charge, but it is outweighed by the increase in shielding effect and size. Both of them are increasing because there are more inner shells which push the outermost shell outwards. But across a period, ionization energy generally increases. I'm saying generally because a couple of hiccups happen and we'll discuss them later. But the reason why they generally increase is because across a period, nuclear charge is increasing and the shielding effect remains the same, which means the attraction for the outermost electrons is increasing, hence the size is decreasing and ionization energy is increasing. That's the overall trend. On the next slide, I'll use the same idea of attractions to explain electronegativity concept. All right. Okay, here I want to discuss the trends in electronegativities. The reason being that the factors that affect electronegativity are the same as what we discussed, even though electronegativity as a concept will be used in a couple of videos later when we're discussing covalent bonding. But I thought I'll talk about it right now also, since the revision, we've already heard this term before. By technical definition, what it stands for is that electronegativity is a measure of the attraction the atom in a covalent bond has for the electron pair in the covalent bond. For example, the electronegativity of H here would be the attraction it has for the pair of electrons that make up the stick, the bond between H and F. And electronegativity for F would be the attraction F has for that pair of electrons. So imagine the stick is 2 electrons. Now each of these will have a different pull, and we know from history that the electrons tend to lie very close to the F atom, which means that F has a greater electronegativity than H, because F has a greater attraction for these shared electrons than H does. And right now we are not studying the effect of this, we are studying why does F have a greater electronegativity than H, or why would any atom have it more than the other atom. For that, we'll study the 3 most electronegative elements that we know of. These are nitrogen, oxygen and fluorine. This is the most electronegative element, then oxygen, then fluorine. Even chlorine below fluorine is not as electronegative as fluorine. So we'll talk about that guy later, but first we'll compare fluorine to the guys before it to explain why this is more electronegative than these two. Now, to understand electronegativity, do understand that when fluorine is attracting the shared pair of electrons, understand that to make this bond, H's outermost electrons would have to have overlapped with F's outermost shell. And that's the most basic way we draw it in O levels. So when I'm drawing it like this, you need to realize that they're sharing overlapping space. So it's basically this electron that's, if you look at the fluorine's shell, I've drawn all the shells here. The nuclear charge is 789, 285, 286, 287 is the outermost configurations. Now fluorine is going to share one electron, so it's going to pair this one up with something else from hydrogen. But realize that when they pair up, the paired electron is sitting somewhere here. So the reason I'm mentioning this section or this property within the same as the other two discussed, like atomic radius and ionization energy, is because the force that these electrons experience from fluorine are the same or similar to the force that fluorine's own outermost electron experiences from itself. And we already have discussed this, that these guys are across a period, and across a period the inner shells remain the same, so the shielding effect remains the same, but the outermost attraction for the outermost electron will increase as nuclear charge increases. So as I go across this list, this is the greatest attraction amongst these three for the outermost electron. What you really must realize is that that same force is the one that's pulling these electrons towards fluorine. So amongst the three in the same period, as the nuclear charge is increasing, the attraction for the outermost electron increases. Even that means it's harder to lose this electron. Also, when the same atom is now going to share to make covalent bonds, the electrons in the covalent bonds are going to be attracted as strongly or more for the guy with the greatest nuclear charge in the same period, because the shielding is the same. So across a period, the same factors which increase ionization energy are also the same factors that increase electronegativity. So yes, all these three are very electronegative, but amongst the three also fluorine is the most, because as you go across the period, the nuclear charge is increasing, which means the attraction for this outermost electron is going to be huge, the most amongst these three, which means amongst these three fluorine is the most electronegative element. So the reason why fluorine is the most electronegative element is because that the electrons it's pulling is very close to the nucleus, and amongst all the other smallest non-metals out there outside of hydrogen, they are the smallest. They are in period 2, least number of shells, and amongst the least number of shells, this guy has the greatest nuclear charge. So even though nitrogen will pull the electron very much, so will oxygen, but fluorine will do it even more. So amongst the three, this is the most electronegative element. And not just amongst the three, even if you talk about chlorine below fluorine, you'll understand why fluorine is the most electronegative element. So I'm going to scroll down to show you that when I compare fluorine to chlorine, and I'm going to zoom out just a bit so I can compare them, is when you go down the group, the electron that the outermost electron chlorine has is further away than fluorine, and because it's further away and has more inner shells, this guy is going to experience greater shielding, and the greater shielding will override the additional attraction from the 17 plus. So the same factors that made chlorine's first ionization energy lesser than that of fluorine's is less than that of fluorine's, which means that the guys that are right here being shared with this electron, that electron is being pulled by chlorine but pulled less than that of fluorine. So let's say I'm using a blue X to mark the electron of hydrogen. So when this is coming close to being shared, this electron, if it's HF, is pulled more by fluorine than the H in the HCl. And the reason for that is the pull that this will experience is less, because even though the nuclear charge is more for this electron, it's going through more shells, therefore greater shielding. And shielding down a group outweighs any effect of increase of nuclear charge. So the attraction decreases. Not much, but it decreases, which makes chlorine less electronegative than fluorine, because fluorine pulling this outermost electron of H is going to have more attraction, because even though the nuclear charge is less, the shielding is even less. So let me use the blue arrow. So this blue arrow here and the blue arrow for chlorine. The blue arrow in fluorine is greater for X than in chlorine for X being the electrons of hydrogen. And the reason for that is down the group, the attraction for the outermost electron will decrease even though the nuclear charge is more, because now there's one extra shell in fluorine. In fact, I think I've written all of these wrong here. These are supposed to be, and I apologize, these are 2, 5, 2, 6, and 2, 7. Please forgive me. Yeah, so that's wrong. So anyway, so comparing these two, what you realize is that fluorine has only one inner shell while chlorine has two. So chlorine has more inner shell electrons, therefore greater shielding. More shielding, less attraction. And I know I might sound like an idiot harping about the same point again and again and again, but understand this is the point that makes it very important about, and this is the same idea that affects every single property that we'll come across. Think about it. Ionization energy affects reactivity of electron loss, losing or gaining, and electronegativity affects polarity of molecules, intermolecular forces, reactivity of molecules, reactivity of organic compounds, and every single thing. So this is the basic foundation of which most organic reactions and a lot of inorganic reactions are based on. Redox reactions, A2AS में पढ़ेंगे आप, group 2 theory, group 17 theory, organic chemistry, all based on the simple ideas of electronegativity and ionization energies, and both of them are based on this nuclear charge and shielding effect and size. And across a period, nuclear charge increases and shielding remains the same. So ionization energy increases and electronegativity increases. But down a group, the shielding effect increases, which outweighs the increase in nuclear charge, which means that electronegativity decreases and first ionization energy increases. So down a group, they become less electronegative but are willing to lose the electrons easier. Across a period, they're less likely to lose electrons and are going to pull electrons more and more, which is the reason why across a period the guys towards the right of the period are less likely to make positive ions but more likely to share electrons, which is why they tell you in O levels that metals lose electrons, which is the guys in groups 1, 2 and 3, because they have low ionization energies, and non-metals, the guys on the right of the periodic table, tend to share electrons and not lose electrons, because losing for them becomes harder but sharing becomes easier because the pull is becoming greater. So that's the basis of our or most chemistry reactions that you guys will see. So this ends today's video. Tomorrow we look at the specifics of ionic radius, and also how the first ionization energy does slightly vary across a period, in addition to just increasing. There's slight hiccups that we'll talk about those two things tomorrow. Thanks guys. Bye.